first comment is about the Comey. No, I'm just kidding. So I know we haven't gotten into the finite differences, and we're doing that today.
Yes.
But I do have a question. You want us to write a program which approximates that Poisson's equation on a linear system, but like, do you care how many values of x that we use?
Oh, like the number of grid points and stuff?
Yeah.
Not at all.
Cool.
If a problem doesn't say, then I don't care.
Okay. Yeah, it didn't say, so I didn't know. Okay.
Yep. Just make something up. I think what I'm going to do, because I just realized when I looked at the material on the MIT site, deciding what point I would stop. So it worked out to roughly one of their lectures per day, and I'm actually a little bit ahead of that, like one day ahead, which I prefer not to be. So, yeah. So you can see that percentage-wise, it adds up to a lot. So I think what I'm going to do is, for the sake of the homework, I'm going to go ahead with covering its finite difference stuff. It's up next, and that will probably take a couple days. So the next part is spectral methods, which is not related to this homework. So after I get through this finite difference stuff, then I'm going to pause lecturing for a bit, so that the focus during class time could be on getting you guys moving with that homework. So we'll see how long it takes. That might be like Monday, for instance. That's a guideline. Yeah, I just made up that day. Yeah. So,
quotes.
Yeah.
Due date and 5 days grace period stuff is kind
I copied and pasted from a previous syllabus. Yeah.
So you'll tell us when it's
Well, because on Monday I will put out the next one, and I figured 10 problems breaks down to roughly 4 assignments, and it's a 4-week class, so roughly 1 a week, just for guiding how to pace yourself. But really, I guess you have to wait until I cover that stuff to get started. The other thing is, I think what happens is I don't have to, because even if a class ends June 30th. I'll have to check on this, but I'm pretty sure I don't have to report grades until the very end of the summer, long before the other classes, like the full-term classes and so forth. You're going to be too busy during July anyway.
Yeah.
So you get moving.
I am.
Okay, all right. Yeah, we'll keep going with that. That gives me some leeway as far as accepting assignments and so forth. So, because depending on what I cover, like the ending material, there might not be a whole lot of time after I cover that and the end of the class to do like whatever the last assignment is. So if it spills, if you guys working homework spills into July, that's fine with me. So. Okay. The only thing I want to avoid, like I said, because this happened some last semester in 610, because I was really, really loose, was to have so much dumped to me at the very end. So, yeah. Okay. Yeah, and I figure that can't be good for you guys either, to be doing so much all at once. So, yeah. So, spread out the pain. All right. Well, there are typos I need to fix in the notes. All right. So now we can. This numerical PDE course can finally get numerical. Starting with the most straightforward types of methods. Finite difference. So the idea is we want an approximation of a given derivative or partial derivative. So, for instance, partial derivative of j partial derivative of u with respect to xj. And right now we're going to assume it's just a function of one variable. It's not really a partial derivative, just a derivative of u at a certain point, x naught. As a linear combination of a certain number of values of your function u at various points, which could include x naught. Now, so the idea is we need to find these coefficients, ai, that will give us as accurate approximation as we can get. So for terminology, this vector of coefficients that we're going to find I'll emphasize my commas here. Okay. That is called a finite difference stencil. Now, for the 1D case, we'll look at, we use Taylor expansion. So we'll call Taylor's theorem. Where this superscript with a parentheses refers to the jth derivative. And when it's j equals 0, so the 0th derivative, then we, that's just the function value itself. Okay. Now, what I'm going to do is I'm going to refer to all of these points, x0, x1, x2, and so forth, as in terms of wherever located relative to x0. So we're going to define xi bar to be xi minus x0. So x0 bar is 0, for instance. And that just allows me to simplify my expressions a little bit. So this approximation that I'm looking for that has this form can now be written this way. Well, okay, I'll do this one step at a time. So I'm going to replace each of these values, u of xi, by its Taylor expansion. And then I'm going to have xi minus x naught to the j. But that's the same as xi bar to the j. Then what I can do is rearrange the sum so that I have derivative values, anything that doesn't depend on I, I'll pull out. And then I have these expressions, sum of ai, xi bar to the j. Okay. Now, the goal is to approximate, so I want this to be an approximation of the jth derivative. Well, wait, let me check my indices here. that the way it is. Okay. So to go back to the original problem, to approximate jth derivative at x naught, well, here's what we need to have happen. That, because here, I'm sorry, I'm getting myself into a notational quagmire. I should realize when I was typing up these notes in the first place. So, okay. Here's what I'll do. I'm going to repeat this expression, except I'm going to make a notation change from here to here. J becomes K. Okay. I see that the recording cut out while I was writing this. So this is exactly this. I've just changed indices here. J becomes K. So I want to approximate this as closely as possible with this. So there's going to be some error because it's going to be just an approximation. Now, so notice this left side here has derivatives of all orders evaluated at x naught, starting from 0 derivative, first derivative, and so forth, but I want to get to derivative j. So that would require the following, that whatever is multiplying derivatives of different orders, so not j, I want whatever's multiplying that to be 0 as much as possible. So I would want this sum to be equal to 0. I'll do it as a brace. I want it to be equal to 0 when k is not equal to j, so that these derivative terms will, with a wrong derivative, will not appear. But then when k is equal to j, this same sum here, what do I want that to equal? To make sure I get that.
One.
I knew someone was going to say 1. That's why I asked it.
It was a guess. I'm sorry.
Okay. All right.
Which part?
Okay. So when k is equal to j, I want this whole expression to have this pop out. I think, Nikesh? Yeah. Or j factorial since k equals j. Yeah, j factorial. To cancel that out. Okay. All right. So this gives us a system, and the thing is, AI are unknowns. So these equations are linear in the AIs. So what we have is a system of linear equations to solve. So if we decide to let k be equal to let's see. So we have well, the total number of points that we're using is m plus 1, because so we have m plus 1 coefficients altogether. So if I let k equal to 0, 1, 2, up to m, and therefore
This isn't a deep thing.
Okay. So what we have is m plus 1 equations for our m plus 1 unknowns to ensure uniqueness. Okay. Now, let's take a look at the system of linear equations that we end up solving. Like, what is the structure of it? What we have is so we solve the system VA is equal to B, where V has this structure where we have ones across the first row, and then we have our x bars across the second row up to xm, and then x bars squared across the next row, and then we have higher and higher powers all the way down to so we have m plus 1 points, so we have m plus 1 columns. And I'm going to let the power of these go up to some unspecified power n. So what we have is n plus 1 rows. And then A is our stencil, our unknowns, which will have n plus 1 elements. And I'm going to specify that n must be less than or equal to m. And the right-hand side, B, has all zeros except in element J, or I should say element J plus 1, because the first equation has everything to the 0 power. In fact, I need to fix that in the notes. Forgot it was 0 indexed. Okay.
And 0 below?
Yeah. Yeah, all zeros except for that one element. Okay. And because we want the J derivative, then n certainly has to be greater or equal to J. Okay. Because otherwise we'd only have a trivial solution. Okay. Now, so for a case where n is equal to m, so number of rows equals number of columns, then there's a unique stencil. Whereas if n is strictly less than m, we have infinitely many solutions. We have an underdetermined system. So then we can use whatever criteria we like to choose a stencil out of those infinitely many. For instance, the most common usage is to ensure higher order accuracy, but then we would just end up going with the square case. But if there's other criteria based on like what produces the most physically reasonable solution, sometimes we want to use that leeway. So that's why I'm allowing the possibility that this is a rectangular matrix. But we definitely want to make sure there is a solution. That's why we must have n less than or equal to m. Okay. So now what I'll do is step through a couple of examples, see some stencils, and these stencils will likely be familiar to you from upper classes. Let's see. Yeah, all of you have taken 772 at one time or another. Okay, Tavish hasn't, but well, these things will also appear in 560. Wow, this thing is recorded for a whole 6 minutes. All right. So, I let J and M both be equal to 1. So, we're using a 2-point stencil, and we're approximating U prime of x naught. So, what we would get is our matrix V is just going to have 2 rows, 2 columns. So we have 1 across the top, and then we have x naught bar and x1 bar. But the thing is, again, and then our stencil A has these 2 values, A0 and A1, and our right-hand side B has 0 and then 1 factorial, which is 1. But the thing is, the way we define these bar values, x naught bar is always 0. And so I just let x1 bar, which is defined to be x1 minus x naught, I can let that be a h. H is commonly used to refer to spacing. So then, the system that we're actually solving is this system, A0, A1 is equal to 0 and 1. Now, so another way, A0 plus A1 is equal to 0. HA1 is equal to 1. So at least in this case, we can easily solve this system. So what are our values for our stencil? Yeah, so 1 over h in the second equation. And in the first equation, they sum to 0, so this has to be minus 1 over h. So that means our approximation of u prime at x naught is equal to, so that's a0 u of x naught plus a1 u of x1. So that would be u of x1 minus u of x naught all over h. Actually, what I can do is I can say this is equal to this as long as I include the error, or at least the order of magnitude of the error, plus big O of h. In other words, the error is proportional to h. And this is called the forward difference. Now, the way you can tell that the error is order h actually doesn't come from the linear system. You can see that from the Taylor expansion, from which we got the system of a u of x1. So in fact, I'm going to show you how we can get the error term more specifically. So u of x1 Taylor expansion around x naught, that's our center, plus u prime of x naught times x1 minus x naught, but that's h. And then we have 1/2 u double prime, and I want to terminate the Taylor expansion here. So this is actually going to be the remainder term. It'll be some unknown point, u double prime of squiggly, h squared, where c, or as I like to call squiggly, is between x naught and x1. So now what I can do is I can rearrange this according to my forward difference. So u of x1 minus u of x naught all over h turns out to be all of this divided by h. So u prime of x naught, which is what I'm trying to approximate, plus 1/2 u double prime of squiggly h. So in fact, the minus this is the error in the approximation. So my error term is really minus h over 2 second derivative at an unknown point. If you know something about the second derivative, you can use that to at least get a bound on the error. But the point is, the error in this case is proportional to h. All right, so any questions about getting this stencil? Now, if I assume that h is positive, and generally we'll do that, this means that x1 is strictly greater than x naught. So we're using a point to the right of x naught to approximate the derivative. But suppose we can't do that. Like suppose x naught is like a point at the far right boundary. So we don't have any information past that point. So we have to use a point to the left. No problem. We can just require that x1 be less than x naught. So what I could do is I can replace h by minus h throughout. And if I go through all of this again, everything just gets negated. Then we have u prime of x naught, turns out to be u of x naught minus u of x naught minus h over h. And then we get the same kind of error term except with the opposite sign, because again, h goes to minus h. So this is the backward difference. And again, the error is big O of h, or what we say is this approximation is first order accurate. Now, give an idea as to we want to have some flexibility where we want to use more points. So I can let j equal 1 still. So we're still looking at approximations of a first derivative. But now I'm going to bump m up to 2. So 3-point stencil. For first derivative. x1 is going to be x naught plus h, and then x2 is going to be x naught minus h. So that means that x naught bar, as always, is 0, x1 bar is h, and x2 bar is minus h. So, in order to ensure that I at least get to first derivative, I'm not approximating any lower order derivative, and there's no term like that, my system to solve is I'm going to have three unknowns, a0, a1, and a2. And by minimum conditions that my stencil must satisfy, well, I have a first row by van der Waals matrix. Actually, did I write down the term van der Waals earlier? I don't know if I did. Yeah. Okay. Okay, let's make sure it's on the record. So we have my x bars to the first power in the second row. So h and minus h. Okay, so any matrix where you have first row, so each row consists of powers of certain x values, starting from the 0 power to the first power, second power, consecutive powers like that starting from 0. That is a van der Waals matrix. There's actually a MATLAB function called vander that if you give it the x values, it will generate the van der Waals matrix for you. And the other thing I want to mention is a van der Waals matrix is guaranteed to be invertible if only if all of the x values are distinct. And well, you can see that if two x values are the same, you'd have two columns that were identical, and that would make it singular. But yeah, as long as they're distinct, it's definitely non-singular. If points are close together, though, then it's ill conditioned. Okay, so, and on my right-hand side, I want the element corresponding to the first derivative to be equal to 1, so it's a 1 factorial for first derivative, and then 0 up here. So this is a system that I need to solve, but there's only 2 rows and 3 columns, so there's infinitely many solutions. And they all have to satisfy, if you were to work through the algebra here, like from the second equation, you would get a1 minus a2 has to be 1 over h. And then, since all of these have to sum to 0, a0 is equal to minus 1 minus a2. So any values that you pick, a0, a1, a2, that satisfy those two conditions, so basically a one-parameter family of solutions, will at least give you an approximation of the first derivative. That will give you first order accuracy. But since we have some leeway in choosing these, we want to use it to maximum advantage. And the way we'll do that is to go for second order accuracy. So we've imposed too few conditions, only 2, on these 3 coefficients in our stencil. So impose a paired equation requires second order accuracy. So now we have a system 1, 1, 1, 0, h minus h, and then b's value squared. And the right-hand side is going to be 0 and 1 for first derivative, and then 0. Oh, copy and paste bug in the notes. I forgot to include that third element on the right side.
Yeah, I was wondering about that.
Yeah.
Like, it should be a 3
Yeah, you think so, but yeah, you're gonna be lots of things to wonder about in these notes probably. Okay, so now when you go ahead and solve this system, so this third equation, you end up with a1 h squared plus a2 h squared must be equal to 0. But then you can divide through by h squared, so this means that a1 and a2 have to be negatives of each other. But then, if you go back to the equation for a0 over there, that's equal to, a0 is equal to minus quantity a1 plus a2. So that tells you that a0 has to be 0. It also tells you that if you go back to the first equation over there, a1 minus a2 is the same as, well, a2 is minus a1, so that's 2a1 has to equal 1 over h. So that leads to the conclusion that a1 is 1 over 2h, a2 is minus 1 over 2h. So now you can write down your stencil that is second order accurate. So now we have the center difference. So u prime of x naught is u of x naught plus h minus u of x naught minus h all over 2h. And you could also see, by using Taylor expansions of both these values, that we have order h squared error. So it's second order accurate. And if you were to take a function which you know the derivative, something like sine or cosine, and try these out for a certain x naught and a certain h, you would see that the center difference is way, way more accurate. So that second order accuracy makes a big difference. Okay. So any questions about the center difference? Now, take it one step further. Let j equal 2, so second derivative. So that's good. Suppose at least we need these 3 equations, so we'll use 3 points. So now our system is 1, 1, 1, 0, h and minus h. Well, actually, I can do this more generally. x1 bar, x2 bar, and then x1 bar squared, x2 bar squared. So this is the Vandermonde matrix for x naught bar, which happens to be 0, x1 bar, x2 bar. These are our unknowns. And then we have, for second derivative, it would be 0, 0, 2. So in the 2 plus 1/3 element, we have to put 2 factorial, which is 2. Okay. So what we're going to get is second order accuracy because the first term that is left out in these Taylor expansions would be of, well, actually, okay, I'll get to that after I write down the solution. So right now we're just focused on solving this, and then we'll take a look at error. So we have A0 is minus A1 minus A2, where for A1 and A2 we can get explicit formulas. So going through the nasty process of solving this system, but what I did was use the formula for the inverse of a 2 by 2, because if you just focus on these two equations, since they don't involve A0, we can solve for A1 and A2 independently, and then use those values to get A0. So A1 is 2 over x1 bar minus x2 bar, and then A2 is minus 2 over x2 bar minus x1 bar. Okay. Now, so at least in terms of your points, you could get a stencil. So what I'm going to try here, just for fun, then kind of deviating from the notes for a bit here. So that's before. I'm going to let x1 bar be equal to, well, I'm going to call it h1. And I'm going to let x2 bar be equal to h2. So in other words, I'm going to assume that the spacings between x0 and the other points, I'm not going to assume symmetry, at least not yet. Also, h1, h2, allowed to be positive or negative. So I'm not making any assumption about that, but that's expressed in terms of spacings. So now my stencil, so u double prime at x0 is approximated by, so I have 2 over h1 minus h2, u of x1, minus 2 over h2 minus h1, u of x2. And then finally, I have, for x0, I'm going to have, okay, so minus a big monstrosity times u of x0. So that's just going to be minus, and then I have a sum of these two. H2 minus H1. Okay. So right now I have my approximation. And notice that all the denominators, like suppose I let H1 be equal to H and H2 equal to minus H, all my denominators would be like to the second power in H, which is not surprising because we're dealing with the second derivative. So what I'd like to do is now express u of x1 and u of x2 in terms of their Taylor expansions around x0. And I want to see what happens to the error. Okay, well actually, right around the halfway point. I'm going to break now because that's not going to be quick. See how the error behaves.
Okay, so I get like that
I'm going to point over here again.
J is your whatever derivative.
Yes.
But like, what's an appropriate choice of M?
Oh, anything that's greater than or equal to J.
Okay, so M is just greater than or equal to J. So is there? So I'm guessing that greater values of M increases your accuracy. I just made that up.
Well, yeah. or it gives you the leeway to do so.
Okay.
Yeah, and that's actually what happened in this. Well, I erased the other half of it, but where I had m strictly greater than j when I was finishing off this example,
Yeah.
until adding in this third equation to get second order accuracy. But I can't rule out that I might want to have some other criteria instead to pick out which of the infinitely many stencils I want.
Repeat that. I'm sorry.
Okay, if m is strictly greater than j, you get infinitely many possible stencils.
Okay.
And in this case, I picked out one stencil by requiring second order accuracy, but I can't rule out that maybe I want to have some other criteria for my third equation to pick out the stencil I'm actually going to use. Because it's not always about having the highest order of accuracy, especially for problems that we'll see toward the end of the class, end of the course, where we have solutions with discontinuities. Because high order accuracy only comes when you have high order derivatives that are well behaved. If you don't have that, then forget high order accuracy. And I'm honestly kind of amazed that some researchers still want these higher order methods for problems for which there's no hope of having it. So in that case, maybe other considerations like what makes the most physically reasonable solution, and that'll become clear later when we get to that. So having some flexibility could be a good thing.
So another question.
Yeah.
For our homework, if we were doing something with a fourth derivative, would it just be appropriate to say, all right, I'm just going to use n equals 4?
Yeah.
Cool.
Yeah, and generally you will. Just let m equal j equal whatever order derivative you're after. Okay. So, is that all your questions? Sure.
Yeah.
Okay. All right. So now, back to the second order approximation that wrote at the end of our break. What I want to see is, I go ahead and expand u of x1 and u of x2 in the Taylor series around x naught. What we should see is anything related to 0 for first derivative cancels out, and we'll see second derivative. But then it's what are we going to see after that? It's what even I am in suspense about. I mean, I pretty much know, but I wanted you guys to see the process of how we work out these error terms and order of accuracy. Okay. So what we have is 2 over, just better have my notes in front of me. All right. H1 times H1 minus H2 times, and what I have written over there is u of x1, but I'm going to replace that by Taylor expansion. U of x naught plus u prime of x naught h1 plus 1/2 u double prime of x naught, which is what I really want, h1 squared, plus 1/6 u triple prime h1 cubed. I'll go out to one more term. So u fourth derivative, and I'm going to make that a squiggly 1. I'll stop the expansion there. Okay. And then for the second term, I'm going to have minus 2 over h2 minus h1, and Taylor expansion of u of x2, which is going to look exactly the same, except h2 instead of h1. Okay. And then finally, the last term is a minus, and then a sum of these two fractions plus, okay, minus rather. U of x naught. Okay. So I want to try to simplify this as much as I can. Now, one thing that will help is these coefficients, because this is a1, this with the minus included is a2, and this with the minus included is a0, and they already sum to 0. That was one of the equations in the system that we solved to get these. So they're all multiplying u of x naught. So all the u of x naught terms have to go away. I'm not even going to work out the algebra of that. We just know it. So gone, gone, gone. So that helps. The next thing is we move on to the u prime terms. Now, here u prime is multiplied by h1, which cancel, and that h1 cancels with this h1. So what we get is 2 over h1 minus h2 times u prime. And then down here at u prime h2, this h2 cancels with the h2 over here. So then I have this bugs me. I'd be so pissed if I screw this up. Because these are supposed to cancel out also. Okay. Yeah. Okay. So I think I know what it's supposed to be. I just need to confirm something here. I'm going to cheat for a little bit. Because I have h1, h2, h1 squared, h2 squared. The matrix needs to be inverted. So I'm going to have the determinant is going to be over h1, h2, h2 minus h1. Okay, and then for the inverse, I need the second column. So I'm going to negate these entries and switch the diagonal entries. And I really only care about the second column multiplied by 2. Okay, so the first element should be the h2's cancel, so I have 2 over h1, h1 minus h2, so that's correct. The second one, the h1's cancel out, and I have 2 over h2, h2 minus h1. Okay, so that should actually be, I'm just going to negate these, or swap these. Oh, okay. And I need to fix the other board. Okay, so that should be h1 minus h2 in both cases. Okay. Now, alright, so that's h1 minus h2. And now we can plainly see those cancel out. So that is gone. So we have nothing with the first derivative term. Then, for the second derivative term, I'm going to have 1/2 h1 squared times this plus 1/2 h2 squared times this all times u double prime of x naught. But now what's going to happen is here we have cancellation of one of these factors of h1, so I have 2's cancel out. Okay, that cancels with one of these, that cancels with one of these, and what's left is h1 minus h2 over h1 minus h2 is 1. So sure enough, our first term is what exactly we're after, u double prime of x naught. Okay. Now, any questions so far? Kind of a mess, I know. Well, I think pretty much all of you deal with bigger messes in your research, so that's some of you have found out already. Okay, so now that we have what we're approximating, the next term involving the u triple prime and the cubes, that's going to be our leading error term. So that's going to be, we'll have a 1/6 out front, and then we'll have a u triple prime of x naught out front, and then all the interesting stuff is going to go here. So what are we going to have? We're going to have h1 cubed over h1. Oh, we have 2's in both, so I'm going to get rid of those right away and have 1/3 out front, just to minimize what I write. So h1 cubed over h1 is going to be h1 squared over h1 minus h2. And then down here we have, okay, I took care of it too, h2 cubed over h2, so that's h2 squared. But there's also a minus over h1 minus h2. Okay, this isn't so messy after all. So that's good. Now, I'll take it out to one more term. Well, that's all I got. So, all right, 2 over 24. So that's 1/12. U to the 4th. And actually, what I'll do is I'll make these x naught after all, and then put a dot, dot, dot for terms that I will never care about, just so I can combine these. Okay. And now I'll have similar thing except cubed. So h1 cubed over h1 minus h2 minus h2 cubed over h1 minus h2. Okay. And then other stuff. Okay. Now, so we have u double prime of x naught plus a couple of error terms. Now, up top we have h's squared. Down below, h's to the first power. So overall, we're looking at first order accuracy here. Second order in this term, and higher orders after that. So, I've not made any choice about how the points x1 and x2 sit with respect to x naught. Are we to the right, to the left, are we to the centered, that sort of thing. So, I'm going to use the error to determine what kind of placement of points is best. And the way I'm going to do that is I want this to be 0. Now, so how should that be accomplished? Well, what? Negative. Yeah, because what I can do is I can combine this, and I'm curious as to whether this is what you did in your head. H1 squared, 2 squared over H1 minus H2, and then you factored, yeah, there's a difference of squares, so I have H1 minus H2, H1 plus H2 over H1 minus H2. Cancel, cancel, so we get H1 plus H2. So, yeah, you set them to be negatives of each other. So, in other words, X naught is in the center, and the stencil is symmetric. You have X1 on one side, X2 on the other side, equal spacing. So, I could let H1 be equal to some value H, H2 is minus H. And that will ensure not first order accuracy, but second order accuracy. So now suppose I look at, so now this will be my error term. And I'd like to try to figure out what that is. So if you look at this, I now have h cubed, and then minus h cubed. Oh, okay. Minus h cubed is minus h cubed. So I'll have 2h cubed up top, and then I'll have 2h down below, so I just get h squared. So that means that the error is going to be, now the thing is, here I have a plus, but the error term, you always write it as u double prime x naught equals the approximation plus the error. So this actually has to be moved to the other side. So the error is equal to minus 1/12 fourth derivative times h squared. So we have, and normally what we do is we terminate the other coefficient at that point, so it'd be u fourth derivative at an unknown point, not x naught. Okay, so u fourth of squiggly h squared. So to summarize, I now have a center difference approximation for the second derivative. Well, any questions about what happened here?
That's a cross out.
Yeah, kind of cool, isn't it?
Yeah.
It's nice when it happens. It'd be cool to put it in paper. After lots of crossing out.
Yeah.
Yeah. Okay, so u double prime of x naught is equal to u of x naught plus h, so this would be x1, minus 2 u of x naught plus u of x naught minus h, so that is x2, that is x1. And what happens is, and all of this is over h squared. So what that means is, if you go back to those formulas for a's, A1, to A0, A1, and A2, and set H1 equal to H and H2 equal to minus H, then your stencil becomes these. Okay. And that's how the standard approximation falls out. Minus this term that is your error. to give a little more rigorous justification about one aspect of the error, this squiggly. Because really what happens is, I was kind of algebraically lazy before, because I wanted to be able to factor stuff out. But ideally what I should have done was left this as fourth derivative at unknown points, different unknown points. So really what you get is, you get u fourth derivative at c1 plus u fourth derivative with c2 over 2. So if you had written the Taylor expansion that way, stopping each Taylor expansion at the fourth derivative term at different unknown points, then this is what it would have fallen out. But this is equal to u fourth at some unknown point in C, where all of these unknown points are within an interval that containing x naught, x1, x2. So if you look at the interval that contains all those points, these have to be in that interval too. And the justification for this is by the intermediate value theorem. So C1 is between x0 and x1. This point is between x0 and x2. And C is actually between C1 and C2. Because the idea is that we've used the intermediate value theorem brought out in other classes for, like for instance, if value of function at one endpoint is, make sure we're getting all this. Yeah. If a value of function at one endpoint is positive and at the other endpoint is negative, you know, and the function is continuous, you know the function is zero in between. Here, it's a situation where whatever function values you have at the endpoints, like if C1 and C2 are your endpoints, whatever function values you have at those points, the function, by being continuous, is going to assume every value in between. The average is in between. It has to be. So that's why you can make this justification. As long as you make the assumption that the fourth derivative is continuous. So that's required for that. So if you have enough continuous derivatives, that's when these error formulas are valid. But in some PDEs, you can't make those assumptions about like the regularity of a solution, and so you might not get the behavior of the error that you expect, and that will be why, because you don't have enough derivatives. Okay. So this is how we can come up with finite difference stencils by using Taylor expansion. And not only can it give us the approximation, because it gives us a system of equations to determine the coefficients of your stencil, but those Taylor expansions can then help you get the error term. Now, when I've previously taught about numerical differentiation, like whether it's a class like 560 or 772, I've shown another approach to getting these stencils. I don't remember what that entails. No, I didn't call them stencils, but yeah, but just getting the coefficients. Another way of getting them that did not involve Taylor series. Well, it may look like magic, but Lagrange polynomials. Yeah, so you would fit your function with a Lagrange Lagrange polynomial passing through values at those points, your x0, x1, x2, etc. And then you would compute the derivatives of the Lagrange polynomials and evaluate at x0, and those values would be the weights. And one disadvantage, you could use that for any order derivative, first derivative, second derivative, you can get these same stencils. Except for first derivative, it's harder to get the error term using the Lagrange polynomial approach. It's actually worked out a nice formula for first derivative. For second derivative, it's kind of messy. You have to do all these things with divided differences. So that's one advantage of Taylor series for this purpose. Okay, now, during the remainder of the time, there's not much of that, but I'll get started anyway. Since we're relying on the finite difference material for the rest of the homework. Poisson's equation. Solving using finite difference. Now we'll look at the 1D problem. Minus uxx is equal to f. And we're going to assume, so things get interesting, boundary conditions. We're going to assume a Dirichlet boundary condition at the left endpoint. So this is on the interval 0 to 1. So at x equals 0, we have a Dirichlet boundary condition. And then at the other endpoint, we have a Neumann boundary condition. We have to figure out how we're going to implement that. And okay, I think I can do this in 15 minutes. Okay. I skipped something in your section, but I'll come back to it when we do 2D problems. Do I have that here? No, I'll work it in at some point. Okay. Now, so what we do is we use a uniform grid. So my points will be x0, x1, x2, up to x n plus 1. So we have n plus 2 points altogether. Now these are, and x0 is equal to 0. X n plus 1 is equal to 1. So each x value is xi is equal to I times h. And my spacing h is 1 over n. Okay, interrupted again. So this is our spacing because we have n plus 2 points altogether, including boundary points. We have n plus 1 subintervals that must be of equal width. And outside the interval, I'm also going to have a point xn plus 2 that's equal to 1 plus h. We're going to need that later to figure out how to enforce the Neumann boundary condition. But these points are actual unknowns, x1 to xn plus 1. We know the value of, the value of u at these points are our unknowns, because we know what u is equal to at this point. It's equal to a. Okay, so we use a center difference for a second derivative that I just developed. So minus u double prime at xi, which is equal to, so negative that, so minus ui minus 1 plus 2ui minus ui plus 1 all over h squared plus error is equal to the value of f at these grid points. And this is for I equal to 1, 2, up to n plus 1. So we're posing these n plus 1 equations on our n plus 1 unknowns. So I'll write down what the unknowns are. u1, u2, up to un plus 1, where ui is our approximation to our exact solution u evaluated at xi. Okay. So this is going to lead to, so I'm going to abbreviate this as, well, actually, no, I'll just leave it like this, f of xi. So what we're setting ourselves up for is a system of linear equations, where this gives us our matrix, and this f gives us our right-hand side, almost. There's still a matter of the boundary conditions to figure out. Okay, so let's deal with the boundary conditions, and then we can write down the entire system of equations that has to be solved. So, because the thing is, here's our dilemma. We want to find these. However, if I just write down these equations to solve them, I'm using values of u other than these, because one of these is going to involve u naught, which is not one of my unknowns. And also u, when I is equal to n plus 1, I'm going to have u n plus 2, which is also not among my unknowns. I have to deal with those. So I have to get a system of n plus 1 equations involving only those n plus 1 unknowns. And anything else is shoved over to the right-hand side. So what helps us do that is boundary conditions. All right, now usually boundary conditions, those are the relatively easy ones to handle. So u naught, which is u of x naught, well, that's just equal to a. So that means that the equation I've written down over there, for a case I is equal to 1, so u double prime of x1, or minus that, is equal to minus u naught plus 2u1 minus u2 over h squared plus order h squared is equal to f of x1. So that's the previous equation of I equal 1. But now I know what this is. That's minus a. So that term I can move over to the other side. So Dirichlet boundary condition handled. But now, what about the Neumann boundary condition? That's a little tougher. So what I could do is approximate my derivative at x equal 1, which is supposed to be equal to c, by a forward difference. Actually, no, this is a backward difference. I don't want to use points outside the domain if I can help it. So this involves only my unknowns. So I could call it good with this. So this is one of my equations. But here's the problem with this is this is lower order accurate. My other approximations are all second order accurate. So by introducing a single equation that is of lower order accuracy, that taints the whole approximation. So my overall solution, which could have been second order accurate based on the other equations over there, well now I end up only getting first order accuracy. So I need a second order accurate approximation to this second derivative, to this first derivative on the right-hand boundary. So what I'll do is, to use a second order approximation, instead of doing this, I'll use a second order accurate approximation, which would be un plus 2 minus un over 2h plus order h squared error. And how I can take advantage of this is I can rearrange this to get un plus 2. So un plus 2 is equal to 2hc, well, actually it's equal to un plus 2hc. So now what I can do is I can use this over there in my equation for case I equals n plus 1 to eliminate un plus 2. So what does that give me? It gives me f of xn plus 1, which is my right-hand side value. So that's f of 1 is equal to, now, based on what I have over there, it's equal to minus un plus 2 un plus 1 minus un plus 2 all over h squared. But now, when I put this in here, what I'm going to get is minus 2un plus 2un plus 1 minus 2ch all over, do a minus there, all over h squared. And what I can do now is I'm going to divide by 2 over h and rearrange a little bit. So what it gives me is un plus 1 minus un over h is equal to c plus h over 2 f of 1. So by rearranging this, I get that. And I wrote it this way because I wanted to compare this equation with the one I had before that was only first order. Notice they're almost the same. What's different is I have this extra term on this side. That's first order in h. So basically what I'm doing is I'm making a first order in h correction to this equation, which has the effect of canceling out the leading order error term. And now in fact, it's cool to look at because un plus 1 minus un over h, what's the error term in that? It's equal to h over 2, well, it's equal to the first derivative at xn plus 1, this is a backward difference, plus second derivative, so h over 2 second derivative at some unknown point, plus other terms. But u double prime is equal to minus f, because that's a solution of our PDE. So, so now you can see where that correction comes from by looking at the error in this, and you can see, oh, that's what I'm supposed to correct. So let's go ahead and actually do that. Okay, there's a backward difference. Okay. Yeah, minus u double prime is equal to f. Okay, so now we have our second order accurate approximation. Now, that's one way to handle it. Another way that I could have handled it and it also ensured second order accuracy. Is using a different 3-point stencil. U prime at 1, which is equal to c, could be equal to minus u n minus 1 plus 4un minus 3un plus 1 all over 2h plus order h squared error. So this has a stencil x1 bar is equal to minus h, x2 bar is equal to minus 2h. So I'm using So I'm using whatever point I want to derivative at and 2 points equally spaced to the left. 3-point stencil, second order accurate. But from a linear algebra point of view, it's better to stick with the center difference approximation that I did over there, for reasons that will become apparent very shortly. So now I can write down my overall system. For u0, u1 up to un plus 1. I know I'm running out of time. So my right-hand side, well, my first equation is just u0 is equal to a. That's the Dirichlet boundary condition. That doesn't really count as an unknown. Then, for my interior approximations, I have this pattern of 1 over h squared times minus 1, 2, minus 1. And on the right-hand side, I'm going to have f of x1. And then I'm going to keep that pattern going. And then I have f of x2. And that's going to keep on going all the way down to the bottom. So for my second to last equation, same thing. I have f of xn. So for the very last equation on the boundary, I have the equation from over there, minus 1 over h, 1 over h. So un plus 1 minus un over h is equal to c plus h over 2 f of 1. So that comes from the, so the last equation comes from the Neumann boundary condition.
So if we had two Dirichlet boundary conditions, we would essentially just not do that last row of the matrix and the vectors at all.
Right.
Right? Okay.
Yeah. So in fact, yeah, we can go ahead, so here's what we can do. Cut down the number of equations. And this is where I'll stop after I write this down. Get rid of the first equation, and then incorporate my knowledge of A into this element and move it to the other side. So I have minus A plus 2u1 minus u2 over h squared is equal to f of x1. I can take this term and move it to the other side. So now my new system is, okay, so I have 2 over h squared minus 1 over h squared, and I have this tridiagonal matrix. And then what I'm going to do is I'm also going to multiply the last row by, well, I need to write the second to last row. I'm going to divide the last row by h. And the reason for that is makes the matrix symmetric, which is advantageous for solving linear equations. You can use like the LT factorization, or actually, I think, yeah, you can use Cholesky in this case. And now our unknowns are A1, A2, well, U, not A. U1, U2 down to UN plus 1. In the right-hand side, the first and last terms have corrections. So the first one is f of x1, so that plus a over h squared for Dirichlet boundary condition. And then it's just f values until the very last row, which is c over h plus 1/2 f of 1. Now, one thing I could do that's not really worthwhile, really, is I could add these last two equations together to have the effect of eliminating un plus 1 also, so you just have a n by n system. But the main thing was here, making it symmetric. That's what really helps. Okay, so that's Poisson's equation in 1D, and we'll talk about more general equations tomorrow. you all keep leaving. I'm just going to point out for the video. I knew that something was not quite right over here. That should actually be a minus. U double prime is still minus f, thus making the whole thing a plus. This is equal to c, because it's supposed to be c plus h over 2 f of 1, and now it is. I've forgotten that when you always have exact equals approximation plus error, and the error term, this backward difference is plus h over 2, but I have the error on the other side, thus this is a minus. So that was eating at me the last 2 days of class. Okay, so the correction is corrected.